Kairouz, who will be talking about one-shot privacy auditing and estimation. Take it away.
Yeah, thank you for the invitation. And I was going to talk about the classical things around privacy, communication accuracy, but that's what I've been doing for the past almost 2 years. So I thought I would talk about something new. So I hope you're not expecting something else. So this is a joint work with a lot of colleagues now at Google. Some of them are academics, as you can see. So Krishna, Alina, Galen, Sewong, and Brendan. And it's going to be about privacy auditing and estimation. If you don't know what these two words mean, it's okay, I'll go over them. And there's the one shot in it because we're going to try to do that with in an efficient way, essentially. So let's talk about auditing. Most of the talk is going to be focused on auditing, but towards the end, I'll talk about estimation and not just auditing and why we might need it. So here's an example of how things can go wrong in DP. Somebody writes a paper, comes up with a new method to train models with differential privacy. They claim that they have found a way to train really accurate models with very strong differential privacy guarantee. So if you look at their method here, it's achieving an accuracy of 98.7% with an epsilon of 0.07. This is obviously too good to be true because it's not true. And there's nothing fundamentally wrong in their approach. Actually, they claim to have discovered a new way to bound user contribution or to do the clipping step that's necessary for DP-SGD. Okay, so just FYI, there were a lot of talks on DP, but specifically for DP-SGD, building on Mario's talk, there's this clipping step that you need, and then you add noise that's calibrated to the sensitivity of whatever you're clipping. So here we're clipping to let's say unit 1. So it turns out that what they were implementing is something very different, which is basically they're clipping the normalized gradient. So this 1 over b here is actually inside the clip. And you can see why this is actually not going to work from a DP perspective. Because the sensitivity is actually much higher. So you're preserving the signal, but you're not adding the noise that's needed to get the privacy guarantee. All right, so obviously one approach for you to find this out is to go to their GitHub and read their code line by line and validate every step to see if it's a faithful representation of the paper, and then say, check, this is correct, I'm going to use it, this is indeed a breakthrough in DP. But this is not something that we can continue to do as new methods pop up and new approaches. So we're going to use auditing, and auditing is going to hinge on a way of looking at differential privacy. This is known as the hypothesis test operational interpretation of DP. Goes back to the early days of DP, really. So the way DP can be viewed here is essentially you have two neighboring data sets, D0 and D1. They differ only by one record, and you'll pick one of them, and you will train the model with DP on the selected data set, and then you'll release the result, the output of the algorithm, to some auditor, and they have the job of deciding if you pick D0 or D1, okay? So what they will do is they will choose a rejection region R, and if the output falls in this region R, they'll say, I'm going to reject the null hypothesis. So I'll say this was trained on D1. And if it's not an R, they'll accept the null hypothesis. Simple hypothesis testing, binary hypothesis testing. And we can prove that DP is equivalent to providing a guarantee on the power of this binary hypothesis test. So if you look at the ROC curve, then there is this pentagon-shaped curve that's dictated by epsilon and delta. Obviously, the attacker would love to operate at this point where the false positive rate is 0, the true positive rate is 1, but it's forcing the auditor to be in that region. Okay, so this is something that is important. If you have any questions, feel free to interrupt me because we're going to build on this. All right, so with this interpretation of differential privacy, people can now audit via what's known as membership inference attacks. They're going to crucially rely on this idea of DP is a hypothesis test. We're going to take a data set. So for this talk, think of this data set as maybe the MNIST data set or EMNIST data set, but it could be any data set. You could even craft it adversarially if you want. And you add to it one, we call it canary example. So it's either a training example or some sort of a model update to get D prime from D. And you will select D or D prime, and you will train your model with DP, with whatever epsilons and deltas you've picked. And then you'll give the output to an auditor who's going to determine whether or not it was, from D, let's say. And you're going to repeat it many times. So this process is repeated thousands, tens of thousands, even hundreds of thousands of times. And you'll assess the performance of this auditor. So every time you run this, the auditor makes a decision, D or D prime. So either that was correct or wrong. And you do it, let's say 10,000 times. So you have 10,000 binary values, 0, 1s, determining if the auditor was correct or wrong. And you'll use the sequence of 0s and 1s to compute the false positive rate and the false negative rate. And then you'll take those things and compute an estimate of the epsilon from them. And there's a way to actually be confident about your estimate to give a lower bound. And we'll touch on it in a bit.
I have a question here. So you're going to trust the person who publishes data with this mechanism to take a delta, or how do you choose your delta?
It's the designer's choice. So again, somebody posted code on GitHub saying this algorithm is differentially private. According to my paper, it achieves state of the art. It beats everything out there. And I'm trying to validate if their algorithm is correctly implemented or invalidated, or invalidate maybe results they gave in their paper. All right.
The D and D prime change across these times, or is it the fixed?
You could change them. There's no need for D and D prime to be fixed. As long as, every time you're instantiating a problem, with the right neighboring data sets.
But then the randomness would also come. That the randomness on the choice of data set also should come, right?
Yeah, I mean, if you change them, the variance of your estimate would be higher, right? So you would need to take into account that. Okay, so this is the general recipe, and it has two issues. One is you need to craft the poison. Yes.
Maybe a stupid question. Sorry. So for any auditor, when you compute those false positive rate and false negative rates, you get a lower amount on that.
If you fix an auditor, yes.
For any fixed auditor.
And technically, you need to design here in this space
might want to make
exactly to maximize the bound here. Yeah, great. Sometimes it's obvious what to use, but sometimes it's not obvious. And where it's not obvious, you need to design a threshold for the binary hypothesis test. Yeah. All right, so one question here is we need to craft this canary training example. And the better of a job we do, the better of an estimate we get. And that's not an easy question. But the even harder, I think, problem here is that we need to retrain the model many, many times. Like 1,000 times is the minimum, but you'll see that people have retrained it 100,000 times. This might be okay if the model is actually very small, tens, hundreds, thousands of parameters. But with today's large-scale models and the hundreds of billions of parameters, we cannot afford doing anything like that. So that's a big problem. Right. I mean, if your job is just to say that this algorithm is correctly implemented, you can do it via that. You might actually do unit testing on the code, testing edge cases, but it depends. Sometimes you only have some API access, and you can train certain classes of models, for instance. Okay. All right. So in this talk, what we're going to be primarily focused on is solving these two issues. And the most important one is this one, the one where you have to retrain the model many, many times. And first, we need to understand where is that coming from? Why do we have to retrain the model many times? The issue here is that we want to be confident in our estimate of the epsilon. So if somebody, for instance, is telling you this model is, or this algorithm is epsilon delta dp with an epsilon of say 0.1 or 0.07 as it was in that paper, you would like to pick here a point that's outside the region that dp gives you, and you want to make sure that the confidence intervals are small enough that none of the edges of this box are touching or overlapping with this region. That's how you know that with high probability, the epsilon is actually larger than what it's advertised. Because you want to be very confident in refuting the claim that somebody is making. And so you might wonder, what is this box and what's the width of this box? Well, I said you have sequences of zeros and ones that you're using to estimate false positive and false negative rates. These are Bernoulli IID random variables, and we have a lot of results on how these things concentrate. And that's how we essentially can derive proper bounds with proper confidence intervals. We use one of these well-known results. But what's very common between them, maybe they have different constants, they all behave like √1/n. And that's why we need the number of samples to be large, because we want the width of this box to be small enough. So for instance, if it was a randomized response that kind of achieves 2,10⁻⁵ dp, but they're claiming that, say that it's 0.8, then this box can be wide. It's okay. If you look at the region of a randomized response here, it's okay. If I could find a canary in this point here, a strong, good counterexample, if this box is wide enough, it's good enough for me to refute that claim. But if I'm using the Gaussian mechanism and it's iterated over many training rounds, which is the case with DP-SGD, the actual region of the algorithm is actually very different. And what you're trying, where it violates that claim, is really in here. And this is precisely why you want this box to be very small, because you're searching for, in this case, very little violations. This is why it gets really hard. It's all about the tails in some sense. For instance, if you look at the paper that I opened with, my colleagues at Google and their collaborators were able to refute that claim via this approach. So they used exactly this membership inference attack to show that their algorithm is achieving an epsilon of 2.79. So they were claiming a much, much smaller epsilon. But for them to be able to do that confidently, they had to retrain the model 200,000 times. So their n here was 200,000. And that was kind of critical for them to be able to make this claim confidently. All right, so one way to overcome this problem is to say, you know what, instead of actually comparing two neighboring data sets that only differ by one record, what we're going to do is we're going to make these two data sets differ by k records, and we're going to test for the presence and absence of each one of them. So in some sense, every time I run, I get k tests as opposed to a single test. So now I have k binary quantities. So I've in some sense expanded my sample size. And you would hope that this would give some improvements. By the way, this idea appeared recently in this paper. There's another paper that Ilya is on as well. Sorry for the missing reference, in a different context under label DP, but it has appeared, is what I'm saying, in a bunch of papers. So this could, in theory, reduce the confidence interval by a factor of 1/k, or √1/k, essentially, and that's great. But the problem with this approach is that now the neighboring data sets are not differing by one record, they're differing by k records. And if we want to be absolutely correct, this goes back to the morning talk by Ilya, we have to use what's known as group privacy. When k things change, it's not just e to the epsilon, it's e to the k epsilon. Again, this is group privacy. So technically now we're not testing epsilon, we're testing k epsilon, and we're in some sense back to the same problem that we had before. We have to be very careful in doing this. All right, so here's how we will try to resolve this issue. First, we'll go back to this picture. We need to somehow form many data sets that differ only by one record. As you can see here, there's a bunch of them. I haven't done anything yet. I'm still training the model many times, multiple times, 3 in this case. So we're not going to do that. Instead, what we're going to consider is a data set that has all the records and then a neighboring data set that just misses one of them. All right, so if you can see here, I still have 3 distinct pairs. So I haven't reduced the number of training runs yet, but I'm just thinking of the problem a little differently. So instead of just adding 1 record and not have it, I have 1 base data set D that has all the records and then K different, let's say, neighboring data sets, each that leaves 1 out. I'm going to call this a leave 1 out construction. Okay. So far, nothing happened except that we're just looking at it a little differently. So the way we're going to now train is we're going to train on this data set that has all the canaries, single model, trained once with whatever algorithm you're using, with whatever DP properties it has. And then the distinguisher will have to check for each canary if it was there or not. Okay. And from that, use the K binary values to estimate the false positive and false negative rates. Now, you might feel a little, squeaky about this. Like, what have we done? What's happening? And there's a big question mark here, which is like, how do we test something that wasn't used when we haven't trained on something that didn't have it? It turns out this is the second or third key ingredient that's going to be very critical. The way we're going to construct these canaries is at random. And we want to pick them, all K of them, from the same distribution so that they're exchangeable. So statistically, they look alike. They're not alike, obviously. Once you've sampled, you have an instance. These things are not the same. But statistically speaking, because they all come from the same underlying distribution, they are exchangeable. So this will be important. And here's one concrete construction that I will be using in this talk, which is I'm going to pick those canary examples, not to be as training examples, but rather as model updates. So think of them as D-dimensional vectors, where D is the number of parameters of the model. And they're picked at random, uniformly at random from the unit sphere. And you can then scale them if the clip norm is different than 1. Okay, so there's a well-defined distribution over the unit sphere, the D-dimensional unit sphere, and I could sample from it very efficiently. So they're choosing uniformly from the unit D sphere. And the test statistic that the auditor is going to use is the cosine angle between the final model and that sampled canary from the unit sphere. So we're going to look at that angle. And this angle is simply the dot product normalized, right? So you look at the dot product between the canary and the final model, that's the output of the algorithm. And then you normalize it by the norms. Then that's the cosine angle. And that's going to be our test statistic. So based on that cosine angle, we're going to either say the canary was in or out. Okay, if it's in, we expect that dot product to spike up because the model would have seen the canary, and so the dot product, these things should be aligned somehow. It's going to be large, and if not, it's going to be small. Yeah, the cosine increases. But now here's the interesting thing. The interesting thing is that if we use this construction, we don't need to train the model on any of these data sets. The reason is we have a closed form distribution for this test statistic without even training the model. So in other words, let's pick one of them. Let's say we pick the first D prime here on this slide. And we're trying to test this red sampled canary. You can essentially write the distribution of the cosine between that canary and the final model, because the final model has never seen that thing that was sampled uniformly from a sphere. And in this case, there's like literally, the proof is so easy to actually figure out this distribution in closed form. And so you have the null distribution, and it's going to be exactly the same for all these D primes. I mean, this is why we need statistically exchangeable this property. Okay, I'm not showing it on this slide, but you take my word. If you can take my word for it, that would be great. You could really find that distribution.
Is final model after training with all the canaries, or is it trained on the white data set?
Yeah, so let me go back to this slide. So we train once, that's why we call it one shot. We train once on all of them, right? So here, when we form a binary hypothesis test for each one of them, we have k binary hypothesis tests. For each one of them, the null is going to be that thing, let's say the red thing, did not exist. We have the distribution of the test statistic in closed form. So for each one of the k binary hypothesis tests, we know the null distribution. And for the alternative distribution, you can get it from here.
Remember, you have the same input data set. The final model can still be different.
Yes.
So if you measure this angle between final model and final, how do you decide this?
Yeah, so there's randomness, right? What I observe every time I run this algorithm, it's not going to be the same, but we know the distribution of the output. So if I compute that test statistic, if let's say the red record was not there, and I'm able to run this training algorithm 200,000 times and look at the cosine angle, it'll form a very clean, very nice distribution that I can pre-compute. Like I know it without even having to run. That's the beauty of the design of the canaries. This turns out to be actually key. Yep.
I guess at this point, I'm not sure what the role of K is. Right? Why can't K be N? Like, why can't I do it for all?
Well, what you want is, sorry, well, why can't K?
I mean, like, why don't I use all of the data as, I mean, why do you specifically pick K, which is less than the, I mean, I guess in this picture, K is 3, right?
Yeah.
So why can't K be just be N?
So you want these records. You want these K canary records to be sampled from this distribution, because this is the distribution that you know the null, the distribution under the null hypothesis for, right? That's one thing. And then the other thing, if you cram in too many of them, if you start putting a lot of them, at one point they start becoming correlated. And depending on the model dimensionality, if they start becoming correlated, then testing their presence becomes misleading. And I'll get to it in a bit, actually.
I'll make another argument why you want to keep K small. It's because it kind of it's like Schrödinger's cat. If you inject too many canaries, you change the object that you are measuring. Like, right? You want to measure privacy of a particular process that works on a realistic distribution. If you start changing that distribution, you're like measuring something else.
Basically, group privacy will kick in at one point once these records become strongly correlated.
No, I don't believe that.
All right.
These are random records. They'll never become correlated.
It's
High-dimensional vectors like the
right. But if D is not very high, if their number relative to D, let's say D is 1,000,000, and I add 1,000,000 canaries into my training set, then obviously there's strong correlation.
not between that. Like group privacy will say that the behavior of a trained model with canaries will change from the trained model without canaries. Yeah. That will happen. Yeah. You just don't want to change it dramatically. Yeah.
I think I'll get to also something that will clarify this. Okay. So yeah, this is important, that it's computable in closed form. And yeah, I mean, we talked a lot about this, so I don't think I need to spend a lot of time, but why are we picking random canaries? I mean, you would have thought that maybe if I were to inspect the data set in the model architecture, I could craft something that's specifically designed to maximize the difference between D and D prime. And I believe that that may be the case, but because of high dimensionality and near orthogonality and high dimensionality, we kind of get that for free. We don't really need to inspect the data or the model architecture to know something about the task and go solve an optimization problem to find the optimal canaries for a specific task or model architecture. So we're arguing here that this distribution leads to strong canaries by design. And that's good. And we don't need to know anything about it. Say, for instance, we need to use it at Google, and different teams are using this algorithm to train very different algorithms on very different data domain. We don't need to sit down with every team and figure out what canaries we want to use for each and every single domain. We don't need to train, for instance, craft canaries for images versus speech versus text, so on and so forth. This is just like random vectors in high dimensional space. It works beautifully for everything. And this is the intuition behind it, because it's nearly orthogonal in high dimensional spaces. All right. So for the Gaussian mechanism, we can actually write a theorem. This is the informal statement of it, which is that as long as you have D and K large, and K shouldn't scale as fast as D, then the estimate that you get from our one shot, so what you're going to do here is basically you have a sum of D-dimensional vectors. So you have your true vectors. Those are the vectors that you're computing the sum query on, and then you add those K canaries and you release the whole thing with obviously the DP noise. And what we can prove is that the estimates that we get from this method asymptotically give you the correct epsilon that you're trying to compute. Okay, so this is just an asymptotic proof of correctness. If we didn't have this, we would have not used this method to begin with. This is not telling us much. This is just focusing on one small, narrow, sum query, and it's making sure that our approach at least passes a sanity check. So I don't want to make a huge deal about this theorem. I just want to say that it works as intended, okay? But this doesn't give us confidence intervals, something that, remember, we actually really needed to be able to confidently give lower bounds on the epsilons. So we need to work a little harder to get confidence intervals, okay?
The asymptotics are here over what, N or?
The asymptotics here are over D. There's no N here, say one shot, okay? So the asymptotics are over D and K. So you let D and K go to infinity, K at a slightly slower pace, and you prove that the epsilon is converging. And this convergence is almost sure convergence, because this is a random process, right? So, all right. So let me now pivot to something that we don't have the paper on arXiv for yet, but it's going to be on arXiv soon, and try to understand how can we generalize everything I talked about so that we get rigorous lower bounds from it. So we need to derive confidence intervals and be confident about the estimates that we're giving. So the first ingredient, or the first step in this process, is to actually rethink differential privacy from scratch, from first principles. And it really isn't that big of a difference, but it's actually very important. So what we're saying is that a mechanism is called epsilon delta lifted DP if it satisfies this thing, which looks a lot like DP. So what is the difference? The difference here is the probability is not taken just over the randomness of the algorithm. It's also taken over the randomness in the two neighboring data sets, D0 and D1, and also the rejection region. So everything can be randomized. All right, so now you have a distribution P over D0 and D1 and the rejection region. And what you want is this distribution over both the randomness of the algorithm and P to satisfy the bound. And what we can show, it's actually not too difficult to show that these two are if and only if. So the classical notion of DP and this lifted notion are actually very equivalent. So what this gives us is that now, instead of picking a point here, we're essentially finding a random counterexample, and we can use that randomness to search over canaries. Okay, so this is how we're going to generalize the slide that we had before. Now we're being very rigorous, so we're not doing just one shot. We're going to actually train more than one model here, but you'll see that it gives us gain. So either you have the k random canaries drawn from a distribution, or the k minus 1, so that you have proper neighboring between D0 and D1. And you'll train the model on either D0 or D1. And then you'll ask yourself if C1 was there or something else, C1 prime. Okay. So here's an example. In this situation, again, it's not one shot. We're going to do it n times. Each time we're going to generate k canaries from a distribution of choice. The one that I presented before is a valid one, but it applies more broadly, so you can pick something else. And then you construct D0, which is, say, your favorite data set, MNIST, with k minus 1 canaries. And then D1 has all the canaries. But now you're going to train two models, one on D0 and one on D1. And then what you're going to do is you're going to compute that test statistic on the, on D1, the model that was trained on D1, with all of those canaries. And then when you're doing the null hypothesis, you're going to generate now new canaries. Those are the things that you actually didn't use, C1 prime through CK prime. And that's how you're going to compute the null hypothesis. Okay, this is all done. I mean, it might seem a little bit too much, but it's all done to maintain that D0 and D1 equivalence that we really want to maintain. Okay, so we're doing n iterations, and in every iteration, we're adding k canaries. Please feel free to interrupt me if this is not clear. And then we will use this information to estimate the true positive rate and the false positive rate. So then if somebody picks a delta, we could compute the epsilon from using this expression. And again, it's important. What was important is we're using the epsilon delta lifted DP notion, and we're using the IID exchangeable canary sampling approach. Now, here's the thing. If these things here were truly independent, then we'll get that root k gain in the confidence interval. But we have no guarantee that these statistics, these Bernoulli random variables, are actually truly independent, right? That's the issue that we're facing here. So that dependence is unknown. So what we can do is we can go back to giving a confidence interval that only depends on n, because the outer loop is n times. So we can ignore the fact that we've added k canaries and just forfeit the gains we get from that. But that's really not what we're after, because if we wanted that, we wouldn't have used the k canaries thing. Or we could use more interesting concentration results for Bernoulli random variables that could have dependence. So they can be correlated. If you go back to your statistics textbook, there's a lot of these second order type result and fourth order results. And without going into too many details, but what we could show is that as long as the correlation between these random variables is well behaved, ideally if it's like on the order of 1 by k, suddenly we reduce the confidence intervals to, root 1 by nk. So we got that extra factor of k that we were looking for. But again, this needs to be well behaved. So now it's a question of, for a specific construction, for a specific application, is this correlation well behaved? Yes or no? And you can try it for the Gaussian mechanism, put all the pieces together. And what you will see here is that, let's say here, the true epsilon is 2. And we're trying to falsify a range of epsilons. Somebody claims it's 0.2 or 0.4, 0.6, so on and so forth. How many samples do we need in order to confidently falsify that, no, it's not 0.8, because the true epsilon is actually 2. And you'll see that if you don't use this trick, this is the curve that shows you how many samples you need to falsify. And then if you use the k canary trick with all those added details, then you'll get good gain. For 0.8, you'll get 16x gain. And then for 0.7 or something like that, you'll get 4x gain from this approach. And again, this is something that is provable in the sense that you can be confident about. You could look at this correlation for this Gaussian mechanism, and you'll see that, indeed, it actually behaves like 1 by k. It's not exactly 1 by k, but it behaves like 1 by k. This is empirical correlation here. All right, so I think I'll stop here. I think we're at time, right? And I'll take questions.
Let's take Peter. Thanks. So while the next speaker sets up, maybe you can do one more question.
Thanks, Peter. Sorry.
Yes. Any questions? Yeah.
A quick, possibly impossible question. I think, so it gives you lower bounds on epsilon. Is there any way to get an upper bound on epsilon?
That was going to be the next part of the talk, which is basically, there are many applications in which we don't want to just audit or falsify. We might want to estimate the actual epsilon, because the DP analytic epsilon makes some assumptions that do not necessarily hold. For instance, one thing we actually saw today in this workshop is that you simply get amplification by iterations, right? You could eventually run the DPSGD algorithm indefinitely, and the epsilon would just not go unbound. If you're going with privacy accounting will tell you the more you train, the more the leakage will grow. But we now have some evidence that that's not the case in practice, right? So we don't fully understand these results yet, and you might want to compute that epsilon and be confident about it. And I was going to show a lot of experiments that we've done where we're kind of confident that we're giving the right epsilons, but we don't have formal proofs for upper boundedness or anything like that. So that's an open question that I think this community of all is best suited to try to tackle. Like, under what assumptions and constructions and classes of adversaries can we not only just give a lower bound and be confident about it, but also show some form of an upper bound?
Great. Let's thank Peter again. Peter is a